Started, and I'm gonna do the screen share with the two people, or one at this point, who is currently online. All right, so there we go. All right, so let me see who's online. I think that's Jordan. Yep, Jordan is online with us. Can you hear us okay, Jordan? You can type your answer. All right, excellent. Okay, so Jordan, if you have any questions, you can ask in the text channel, or you can just use the voice channel to ask too. I got you on speakerphone here, so if you need to ask any questions. Cool. All right. So I did fix the program. As it turns out, I was reversing the order. Um, so if I say n is m plus one, that works. Because m is going to be one fewer or one less than n, and this actually does work. So now I can actually ask these questions of how many generations are between Homer and Howland, and so it can solve that and say it is four, which is kind of cool. So this is going to be a basis of how we can determine the cousinship. Because if you want to figure out whether someone is a third cousin once removed or something like that, this would be a basis for that. So I'm going to keep the program around, even though it is not going to be the focus of today's lecture. Now, given we can do something like this, um, even with just kind of the basic Prolog features that I have talked about here, we can use Prolog to find the length of the shortest path between vertices. It would actually be possible. The method to do it is a little bit convoluted because it doesn't have the ability to keep track of the functions, the L value, in the case of Dijkstra's algorithm and stuff like that. But there are ways to do it. So I'm going to work on some of those things, so that next class I can show you, how to use Prolog to find the length between two vertices, even though it doesn't really show you the actual path, but it will still be able to figure out the length of the shortest path. So that kind of concludes, what I want to talk about, regarding predicate calculus. So what we'll be doing today is to talk about time complexity. And there's a lot of symbols and a lot of math definitions, when we talk about this one. But there's a certain importance when we want to talk about your big O notation, because it is used a lot when you want to compare algorithms. For instance, we have sorting algorithms. We have a lot of different sorting algorithms. And if you want to get entertained while studying those sorting algorithms, you can look up Hungarian dance. Okay, and I can see people just writing that Hungarian dance. That's important because it is okay. Because they use Hungarian dance to show you bubble sort, insertion sort, quick sort, and so on and so forth. Um, so how do you choose a sorting algorithm? Well, the first factor is how fast is that sorting algorithm. So we have mainly two different classes of sorting algorithms, one with a complexity of n squared, and the other one with a complexity of n log n. So one would basically grow proportional to the size of the problem squared, and one would grow, proportional to the size of the problem times the log of the problem. So what difference does it make? Well, it doesn't make a difference when n is small. So when n is small, they all work. Okay, no big deal. But when n is larger, you would always be able to find a value of n, such that a more optimal algorithm would beat a less optimal algorithm. Even if the more optimal algorithm is running on very old archaic hardware, it will still be able to beat the other algorithm because of the time complexity difference. Are we kind of doing okay so far with these general topics? So what this module starts with is a very detailed look at time complexity. So I'm focusing on just this algorithm here. This is a very simple algorithm. I would not even call this an algorithm. It's just a quick and easy way to find the sum of the elements of an array. So we start off with an array called A. It has got n elements in it. We have a local variable sum, an index variable I. All I want to do is to find out what is the sum of all of the elements within the array. Okay, it's pretty easy. We start with index 0. The sum is initialized to 0. And as long as I, which is the index through the array, is less than n, we just say, okay, let's pick up one element, add the value of that element in the array to sum, and increment the index I by 1, move on to the next iteration, and keep doing the same thing until I is no longer less than n, which means when I is greater than or equal to n, at which point I is no longer a valid index into the array, and then we can just exit the loop. Okay, pretty simple stuff. But if we want to find out how long exactly this algorithm will take to execute, then it gets a little bit tedious. Now we have to say, okay, how many times are we running a particular line? So line 4, definitely just once, because it is a one-time initialization before we get into the loop. Line 5, kind of the same deal, just once. Line 6 is a tricky one, okay? Because, this is the portion of line 6 that's going to take some time to execute. It's the comparison between I and n. But how many times do we have to compare? What do you think? It's n plus 1. It's n plus 1 because there are n valid indices, but we also have to bump I just past n minus 1 for the last iteration in order for me to exit the loop. So the number of times that we perform the comparison on line 6 is actually n plus 1. Okay, now is that plus 1 really important? No, not really. But if we want to get the exact amount of time to take to execute an algorithm, we kind of have to take that plus 1 into consideration. When we look at line 8 and 9, those would only execute n times because we only got n elements in the array. So the body of the loop will only go through n times. So now, if we want to find out exactly how much time it takes to complete the algorithm, and we'll call that function f of n, it's going to be t1 plus t2 plus n times t1 plus t3. And then the t1, t2s are defined in the previous paragraph. So basically, we look at t1 here. So line 4 and 5, which are the initialization, combined is t1. And then line 6 is the comparison. We execute that line n plus 1 times. Lines 8 and 9 execute n times. We'll use t2 to indicate the amount of time for each time line 6 executes. So that's why we have an extra t2 out here. And then t3 is referring to the amount of time for line 8 and 9 to execute. And we perform line 8 and 9 n times, and that's why t2 is also within this multiplication. T3 is inside this multiplication. T2, which is the amount of time that takes for the comparison, is also inside the multiplication. So that will give you the exact time. But is it really exact? How exact is that time? Well, actually, it depends on a lot of factors. Because it also depends on caching, because modern computer architecture has caching. It also has DDR, double data rate type of memory. So a lot of factors would actually kind of change some of these constants, a little bit, depending on the other conditions, when you're running the algorithm. So if something like this already has a function that gives you the exact amount of time like this, then you can kind of imagine for more complicated algorithms, it's going to look a little bit more hairy. For instance, the time complexity of a bubble sort algorithm boils down to T1 sum T1 plus sum T2 times n plus sum T3 times n squared. Okay, Now, exactly what is T1, T2, and T3? Well, it kind of depends on the actual implementation, depends on the architecture, depends on memory bandwidth, and so on and so forth. So we don't really care about what is exactly T1, T2, or T3. We just know that, okay, it's proportional to n squared times T3, and so on. So here I state that it is tedious to compute the exact amount of time of what a particular implementation of an algorithm is going to take to execute. Most of the time, that is not super important, okay? Because when you are comparing algorithms, for the most part, you are actually comparing the time complexity, which means hopefully you will find one that will always be faster as long as n is large enough. Are we doing okay so far with this? Okay, all right. So section 2.2, basically says how do we compare algorithms? Because if you choose the wrong algorithm, it's going to slow everything down. Even though it might seem to work in simpler cases, in larger test cases, it's not going to work, very well. I can give you one example of why this is important. Back in, I'm remembering what the year was, more probably 1992 or 1993. So that was a long time ago, okay, exactly 30 years ago. So exactly 30 years ago, I had a laptop computer made by not Lenovo, it doesn't have Lenovo as the brand, it was IBM at the time. So it was IBM ThinkPad, so I had one of the original, like the first ThinkPad that ever came out, from IBM. It looks like a brick that is painted black, okay? So they kind of continue the tradition, these days with the black, design. I cannot even remember how much this drive space it had. Probably around 20 megabytes. Okay, you guys are thinking, did I hear it right? 20 megabytes? Because I think my little SD card has like 64 gigabyte, and that's like a super dirt cheap one. Okay, yes, you heard right. 20 megabytes. It had a black and white screen. It was not even color. I was using it to type my dissertation in Word, like Microsoft Word, the word processor. I believe it was version 2.0. And then you ask, how does that have anything to do with time complexity? So in my dissertation, I have a lot of cross-referencing. So I would name and number all the equations, and then later on, I would mention and go like, okay, refer to equation blah, okay, for this blah blah blah, okay. So there's a lot of cross-referencing, which you would not think as anything special. It's like, how hard can that be? My dissertation was only 60, maybe 70 pages long, and that's like double space using 12-point font, which means not really that much content, okay? I remember at one point in time, Microsoft Word was not able to um, basically renumber all the pages. It would start the process, and it would just hang. And it was eerie because I was so afraid that I have lost my entire dissertation. It didn't quite lose it. It just lost. It just could not recompute the page numbers, the references, and whatnot. I have no idea what happened, but I'm fairly sure that somebody chose the wrong algorithm. So the time complexity is just insanely high because that person tested the algorithm on a very small test case, worked okay, and chose the algorithm and go like, okay, it's working fine. So this kind of shows you why it's important to choose an algorithm of the right complexity or time complexity. So is that okay? I mean, are there any questions about this little example? Okay. All right. So other types of sorting algorithms, such as merge sort, they have a time complexity that looks like some kind of T1 plus n times T2 plus n times the log of n times T3. So in this case, each implementation of each algorithm has its own set of the constants T1, T2, and T3. And in this case, I can also kind of illustrate this using an example. Have you guys seen those mainframe computers from the 60s? Okay, they have a very small amount of RAM. So if you look at the actual amount of RAM in those mainframe computers, it's tiny. But when you look at the volume of data that they have to process, it's gigantic. So how do they get the job done? Okay, let's just say that we have one tape that has all the records, and I need to sort the records. But the volume of data of that tape is 1,000, 10,000, 20,000 times of the capacity of RAM of the same computer. So how do you sorting when you can only store a very tiny fraction of all the data that you're supposed to process? Okay, so think of that as the first question. Okay, or first scenario. The second scenario is bringing us back to 2022 or the end of 2022. We got all of these fantastic processors, tons of RAM. Okay, if you get a gaming computer, you can probably install or have ones that have 32 gigs of RAM installed. So most likely you can actually fit everything inside and to perform the sorting algorithm. So let's just say that in both cases you're trying to sort the same number of records. Using merge sort, which was invented almost exclusively for tape operation, is n log n. Using bubble sort, it is n squared. But so I now want to compare the speed of a mainframe computer from the 60s, having all the records stored on tape mechanically. They have to kind of watch the whole thing turning and turning and turning like that. And then the other one is using a modern computer. Everything fits into RAM, and you're running the bubble sort algorithm on the computer. When the number of records is low, the PC is going to win, just because it's a lot faster compared to the mainframe computer. The mainframe computer doesn't really need to be very, the limit has to do with how fast you can move the tape, because it's a mechanical device, and you can only turn a tape, or you can only make the reel turn at a certain speed, because any faster than that, you're going to break it. You're going to break the tape itself. So you can't really move it beyond a certain speed. So just for argument here purposes, let's go ahead and take a look at some numbers. I'm trying to find my spreadsheet, and not this one. We can look at this one, and we'll just open a new tab here. So this is N. This is the mainframe computer. Okay, so I call it mainframe here. And this is the PC, which is a modern day computer. And I also want to look at the factor, of how fast the PC is compared to the mainframe computer. So using Moore's law, okay, what does Moore's law specify?
Isn't it like computing power doubles every
18 months? Yeah, so it's not quite computing power. It states the density of transistors, which roughly translates to the speed and capacity. So doubling every 18 months, that is correct. So from the 60s, okay, just for the numbers to be even, let's assume this is 1962, okay? So compared to today, how many years have passed, or I should ask, how many 18 months has passed since 1962, same day of the year? 60 years, right? 1962 compared to 2022, 60 years. So within 60 years, how many 18-month cycles have we gone through? 40. Well, 1.5 is the factor. So 40 times 1.5 is 60. So 40. So we have gone through 40 cycles of Moore's law. What does that mean? Well, that means if you assume Moore's law is being held this entire time, for the same money, a computer today is 2 to the power of 40 uh, the amount of processing power or the speed compared to a computer in 1962. It's not 40 times, it's 2 to the power of 40, which is a pretty big number, right? So, so we'll use that as a factor. So we'll say factor here. It is 2 to the power of 40. A pretty big number, okay? So now we look at, if you have only one record to sort, the mainframe computer, let's just say that what the amount of time taken to sort one single record for the mainframe is 1. And then the PC is just going to be whatever this number is, but you have to remember to divide it by the factor, which is this number over here. So that's a huge difference. We'll put a dollar sign here because I'm going to repeat the equation over time. So now we look at 3, and you might ask why we are skipping 2. Well, there's a reason why we are skipping 2, but let's look at 3. So the mainframe computer is going to look at, it would take 2 iterations for the mainframe computer running bubbles, not merge sort. It would take 2 iterations. So with the PC, it is proportional to the number of, it's proportional to the square of the number, to the square of n. So in this case, it's going to be, okay, nope, that's not what I want to do. Okay, so it's going to be whatever this number is times whatever this number is, but we have to also, divide the whole thing by the speed factor. All right. So the next number, what do you think the next number is going to be? How, okay, I'm going to tell you what it is, and you can guess the next one. Okay, so this is going to be 7. And for the mainframe computer, it would take 3 iterations for merge sort to get the job done. For the PC, it's going to take 7 squared divided by this factor here. Are we doing okay so far? Okay. So this is just a unit of time. I really don't care what unit we are talking about. I just know the factor difference between the 2 computers. So what would be the next one? Have you guys figured out the pattern? 15 is correct. 15 because it's twice of whatever the number is before plus 1. Okay. So now we have this number times 2 plus 1. And the mainframe computer would take, I'm wrong here because I forgot to multiply n itself. This is the log of n, but I have to multiply n as well. So we have to say 2 times 3 in this case. 2 times 3 equals, okay, go back here, put an equal in front of everything. There we go. And this is going to be 7, which is n, times the log of 7 in this case, which is going to be 3 because I'm using log of 2. Which base I use doesn't really matter. In this case, I'm just using log of 2, but I have to remember to use it consistently. So in this case, it's going to be 15 times, I think 4 this time. So 1, 2, 3, yep, this is 4. And this is growing by the square like that. So when you look at these numbers, you would think, there's no way the mainframe computer can catch up with the PC. But it really is a matter of time. When is the mainframe computer going to be faster compared to the PC? It will take you a lot of records, but the way the curve is growing is very different between the 2 computers. So one is squared, which means it looks like your typical, um, there's a term for that, parabolic curve. And then the other one is a little bit super linear. It is a little bit faster than linear, but when n gets larger and larger, it's almost like it is just linear because of the log n is growing very, very slowly when n is becoming larger and larger. So eventually, they would cross path, and then after that point, the mainframe computer is going to be faster. Okay. Now we can actually use equations to solve what n is going to cross over, make these two cross path, but they will eventually cross path. This one, this example is a little extreme because of the factor difference. So are we still understanding this okay? All right. So um, so now we have to look into how we express time complexity. And to understand how time complexity is expressed, you can go to Wikipedia and you can just look up your sorting algorithms. I'll bet you the first link is going to Wikipedia. Nope, it's not. Okay, I'm surprised. But when you go to Wikipedia, they would give you the sorting algorithms, and then for each one, it would also give you the time complexity. So the time complexity typically would give you the best case time complexity, the worst case time complexity, as well as the average time complexity. So we have a bunch of really good algorithms that are n log n in all three cases. And then we have some sorting algorithms, the insertion sort, selection sort, bubble sort. Those are all with n squared as a time complexity. The best case is not really particularly useful because the best case in some cases is I'll give you an array that is already sorted. What is the whole point then, right? There's no point in considering the best case. So you typically want to look at the average case and also the worst case when you want to choose a sorting algorithm. So what exactly is n squared here? What exactly is n log n? What do they mean? Well, we know it's a proportion kind of thing, but exactly what does it mean when we want to say it is a proportion kind of thing? So that's kind of what we want to understand today is the terminology in order to help you look at all of these numbers and find out how to compare between these algorithms. If you want to ask me what is my favorite sorting algorithm, I have to say it is merge sort because merge sort is it's interesting, it's easy to do by hand, and yet at the same time, it is surprisingly fast, even though it does not seem to be fast. How many of you have studied or at least know what merge sort looks like? Did you guys study the in-place one or did you study the not in-place one? An in-place merge sort means you're basically doing all the rearrangement within an array. So that means everything has to fit within the array first. The other one works on tape. So you have one tape coming in, and you split it into two tapes as the output. And then you take the output tapes, you turn them around, they become the input, then you merge them back into one single tape. So you basically split, merge, and the number of times you have to do the split merge is log 2 of the number of records, guaranteed. Even if the original array is sorted in the opposite order, it will still only be taking log 2 of the number of records of times to do the split and merge operations. Now, each split merge is proportional to the number of records because you have to go through all n records to split into the two output tape. And then the merge is going to end up merging the two tape back into one single tape, which also has n records. So that means the length of time for each split merge is going to be proportional to n, but the number of times you have to perform that is proportional to the log 2 of n. And that's why the algorithm has a complex time complexity of n log n. Is that okay so far? All right. Yep.
What does it mean to be stable?
That is a good question. I am not sure. I just pop into this page as I get here. I think stable may be just talking about whether um, it would do the same thing regardless of what the input looks like. Because I know quicksort depends quite a bit. It depends on which variant of quicksort you're talking about. With some implementation of quicksort, it depends on where the pivot point is. So if you choose the pivot point or if the original content is different, it can greatly affect the actual amount of time. Merge sort does not care at all. So that's why with merge sort, it is not, it is stable. With some other, like bubble sort also does not care. Um, Insertion sort also does not care. I do not know much about what is intro sort. I know what is heap sort. So heap sort, once again, kind of depends on how the data is originally arranged. So let me, stability. Okay, so here, this is how stability is defined. Stable sort algorithms sort equal elements in the same order that appear in the input. Okay. All right, so this is okay. This is not related to the content of this class, but I think it's a good exercise for me to explain what is understanding. Because if I read this sentence here, I understand every single word. Does that mean I understand the sentence in the context in which it appears? Not automatically, right? Okay. So now we need to dig into this. Okay, I want to dig into it because I want to kind of pursue, what exactly does that mean? Okay, stable sort algorithms sort, okay, I understand that part, equal elements in the same order that they appear in the input. Okay, so equal elements, I think refer to elements of the same value. Yep, I think that's what it's referring to. So equal elements means elements of the same value. So if they appear in one particular order in the input, they would also appear in the same order in the output. So whether it is important or not, kind of maybe, maybe not. Okay. So if you think about the Hungarian dance, okay, have you guys watched that video? Those videos of Hungarian dance, demonstrating sort algorithms. Okay, I see one nod. Yes. Oh, I thought you had a question. No. Okay. So I will just kind of briefly go over there because it is relevant in this discussion because then we can find out whether something is stable or not, or at least we can get a visual um, presentation of whether something is stable or not. So we just have to look at Hungarian dance sorting algorithms. There we go. So we got at least three of these. We got quick sort, bubble sort, heap sort, and what else? Insertion sort, merge sort. Let's look at merge sort. And this one is Transylvanian Saxon folk dance. And it looks like it's emulated. I want to look at real people dancing. There we go. Quick sort with Hungarian folk dance. There we go. And I probably want to stop recording right now because YouTube is going to say I have infringed on somebody else's video. We'll see. So this guy is being the pivot. All right, so I think that's enough to make the point that I need to make. So the question is, with a stable sort algorithm, if I got two people, of the same number, those two people would be, we would be preserving which one is first and which one is second after the algorithm is done sorting. I think that is how they define, whether an algorithm is stable or not. Is that okay? But that also points out one thing, right? Because what it does point out by looking into this one single sentence here is the ambiguity of English. Because equal elements can also be interpreted loosely as equal number of elements. So are they referring to equal number of elements, or are they referring to the value of elements being equal? That you have certain elements within the array that have the same value. The context would suggest that we are looking at the value instead of the number of elements, because a sorting algorithm cannot change the number of elements. That doesn't make sense to me at all. So that rules out the interpretation of referring to the number of elements, which leaves behind only the possibility of we are looking at the value of elements. Is that okay? All right. So this is just a brief explanation of why sometimes it is important to use mathematical notations. But to use to use mathematical notation to express stable is actually going to be a little bit cumbersome, because we will have to um, find a way to specify the original order, like the indexes, which one is greater than which other one, and then we also have to use the function, concept, because we're looking at a bijective function to map the incoming indexes, who has which index, to the outgoing indexes, who has which index, and then we have to be able to say, if two elements have exactly the same value, the incoming index has to be in the particular order, and then the outgoing indexes also have to be in the same order. So it's going to take a little bit more work to express the same thing. But this sentence by itself is ambiguous. And of course, you guys are thinking, well, this is Wikipedia tag. You can go ahead and just make it more clear. Yes, I understand that too. All right, cool. So now we're getting back to the module. And I have an example here which is not quite as extreme as my other example in the spreadsheet. So but it's just an example of how eventually a quicker sorting algorithm will beat a slower algorithm, even if one is running on a super fast computer and the other one is running on a super slow computer. All right, moving on. We are now going to look at terms, okay? But before we look at terms, we're going to look at asymptotic estimates, which is basically a way to say, well, as n approaches to become really, really large, what is the behavior of a particular function? So we are not looking at a specific value, we're just looking at a trend, okay? Can we say something about the trend of a function as n becomes larger and larger? And that requires a few definitions. So section 3 itself says, let f of n be the actual time complexity of an algorithm. So that means f of n tends to be kind of be ugly. Okay? Because what we understand as big O of n squared may contain n times log of n, may contain 1 divided by n and other components. Even though they do not matter, they are still a part of f of n. So f of n itself can be very ugly with a lot of different components. And then we also introduce g of n. So g of n is an estimate, okay? It is usually a lot simpler compared to the actual f of n. So g of n is a very simple function as an approximation of the time complexity of an algorithm. So the question is, how do we relate f of n, which is the actual time complexity, how does it relate to g of n, which is a very simple function, and we want to use it as an estimate? Is that okay so far? In other words, we want to be lazy, okay? We don't want to figure out the exact amount of time. I just need to know the trend, okay? And that's what g of n is trying to say is, okay, this is the trend, and we don't have to figure out all the details of f of n. Are we still doing okay so far? All right. So now we have to introduce a few concepts, and they are not 100% necessary, but they're kind of important. At some point in your computer science, career, they can be important. So the first term is called supremum. Supremum is basically, okay. Let me go through the definition, and then you guys can tell me what it reminds you of. Okay. So the definition requires a particular set A, and it is partially ordered using a specific relation. And that specific relation is less than or equal to. So this is what I mean by not intentionally um, comprehensive, is a lot of times when we try to express more complex concepts, we have to use the earlier part of this class as a vocabulary in order to express those things. So in this case, I'm defining less than or equal to as a partial order relation over A. Is that okay? Roughly, it basically means for certain pairs of elements, I can tell you which one is less than or equal to which one, but there are certain pairs between the elements in A that I cannot give you any idea of which one is less than or equal to which other one. That's basically what it means to be partially ordered. But you can also go back to the definition of partially ordered from the relation module. And how many people still remember what that means? What does it mean to be partially ordered? Okay, the easiest one is transitive. It has to be transitive, it has to be reflexive, and it has to be anti-symmetric. Yep, so those three are necessary conditions to become, well, when they combine, it becomes a sufficient condition to define partially ordered. All right, so now that we have A as a set, that it has a bunch of values, and those values, are partially ordered by the less than or equal to relation. So that means, A doesn't even have to be a set of numbers. It only has to be a set of certain elements, and we define less than or equal to as a partially ordered relation over A. That's all we need in order to define these terms. The next thing we do is we pick up a subset X of A, and it can be the same as A, but it doesn't have to be. So X has some of the values of A. Let us define the predicate of P of Yx to be for all X for all lowercase x in X, X is less than or equal to Y. So I'm going to pause here, and then we'll take a quick, closer look at what P, Y, X really means. Okay, this particular term here. So as I said a little bit earlier, P is a predicate, which means it is a function that returns a value of either true or false. I mean, a predicate is just a fancy term for any function that returns true or false. But what is it exactly saying? It's saying, if you give me any element of X inside the set X over here, X is going to be less than or equal to Y. But doesn't that just say that Y is the maximum of the values in X? So now we have to be hair-splittingly accurate about this particular predicate. So let me ask you this question. Does that mean that Y is the maximum of all the values in X? Okay, so I see one person turning the head and go like, no. And what makes you think it is not the same as a maximum?
It can be a value that isn't in X.
Exactly. So y doesn't even have to be in X. In other words, okay, I can give you one example, okay? Let's just say that X as a set has 1, 2, and 3 in it, okay? And the set A would be the set of all integers. So obviously, the set of 1, 2, and 3 is a subset of all integers, okay? We have established that X is a subset of A. Y has to be coming from A, but no one says Y has to be from X. So if I say P of 27X, it would be true, because 27 is greater than or equal to 1, 2, or 3. It has met the requirement. So P of yx is not confirming that y is the maximum within the set of x. It just says that y is greater than or equal to everything in x. Okay? So it's important to note these kind of quote unquote minor differences, because sometimes it makes a big difference in terms of how we use it later on. So the next sentence really kind of spells this out in a better way in English, because all it says is y is an upper bound for x. That's it. Y is greater than or equal to everything in x. And therefore, I guess the word or the phrase upper bound is kind of intuitively descriptive in this case. Are we still doing okay so far with these terms? Okay. So now we actually define what is the supremum of something. So now we define this value s here is the supremum of x. And how is it defined? Well, the if and only if is typically how a particular math concept or notation is defined. Is this is true if and only if blah 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 blah. Okay, so this is the definition of what is a supremum in this context. All right, so we'll take a look at this part here, this part here, and ask, what exactly does that mean? The first part is easy. PSX means S is a upper bound of X. We got that, okay? Just because we know what the predicate P really means in this case, it just means Y is the upper bound of X. So in this case, S is the upper bound of X. Got that, okay? That's the easy part. The second part is quantified, okay? So this is another example of going back to an earlier concept that we have talked about in this class. So we have a universal quantifier that says for all s prime, okay? For all s prime, this has to be true. Okay, what has to be true? This is an implication. What is inside the quantified expression is an implication. So the first thing you want to ask in this case is, what are we ruling out? Okay, what values of s prime is irrelevant in this entire discussion? Well, p of s prime x has to be true for the other one to be meaningful. So that means if s prime is not by itself an upper bound of x, I don't even care. Is that okay? Because as an implication, if the left-hand side is false, the implication is true anyway. So that means what really matters is I'm looking at all of the other upper bounds of x. Okay, s prime has to be an upper bound in order for this part to be meaningful. What is that trying to say? S, which is the supremum of x, has to be less than or equal to s prime. So that means the supremum of x is the minimum, quote unquote, of all of the upper bounds.
It's the second upper bound.
It is the smallest of all the upper bounds of the set x. Doesn't that make it the maximum of x? No, not always. Okay. So note that supremum of x may be different from the maximum of x. This is because the supremum needs not be an element of x, but the maximum needs to be an element of x. And also because A does not have to be totally ordered. It can be partially ordered. So when something is partially ordered, weird things can happen. You may not be able to find a maximum, but you can say whether something is an upper bound of something, of a set of values or not. But for all practical purposes in this entire discussion, if you don't want to look at supremum as a complicated definition like this, you can kind of, okay, just remember the tech is going to cringe, but you can kind of look at the supremum as the maximum. Okay, if it makes it easier for you to understand the rest of the concept, you can kind of make those two things kind of the same, because within the context of this discussion, they would be the same thing. The reason is, what do you think A is going to be when we are talking about time complexity? Okay, what is time complexity? What is it trying to do? We're trying to compare the amount of time it takes for an algorithm to get this job done, right? So the amount of time is what? Is a number, is a real number, right? And if you look at A as the set of all real numbers, in a set of real numbers, the less than or equal to relation is totally ordered. And when it's totally ordered, then the supremum of something, of a particular subset, will be the same as the maximum of that subset. So that's why for all practical purposes, supremum is really maximum. And then we define infimum, which is the opposite. So you can look at it as the minimum. Is that okay? So now we have defined a weird way to say the maximum and a weird way to say the minimum. Are we good so far? Okay. So now we have to look at the limit of a sequence. This class has a prerequisite of pre-calc, and I'm hoping that they do talk about the concept of limit in pre-calc. Is that true or not? Okay, all right. So that means now we can look at a sequence. Now, what is a sequence? A sequence simply means there's a bunch of numbers, and they are sequenced. Now, is it an infinite sequence or a finite sequence? It should not matter. Okay, so whatever we are working with here should also work with a sequence that has an infinite number of elements. Are we good so far? All right. So you can look at the sequence, by the way, you can look at the sequence as an array, as a vector, except it may not end. It may have an infinite number of elements in it. All right, so if I want to say something like this, okay, as I approaches, or the index I approaches infinity, the limit of xi is k. What do you think that means? Okay, we can look at this from the intuitive perspective first. So what would be the intuitive way to describe the limit when I approaches infinity, x of I is k? How would you describe it? Just using plain English.
As I gets larger, the value of x gets closer and closer to k.
Yep, that's the best way to describe it. Okay, as I gets larger and larger, the x of I gets closer and closer to k. Okay, so but that's also a kind of vague way to describe this, and that's why we have a more mathematical description to say exactly the same thing. Well, I shouldn't say exactly the same thing, but to say the same thing, but with more precision. So this is the way we describe it. This is how limit is defined. So this means that k is a unique value that satisfies the requirement. This is the requirement. This is a little bit long because we have nested quantification. In fact, it's nested like 3 times. So the outermost quantification is saying for all epsilon that is greater than 0, and epsilon is just going to be a real number, okay? So you just pick a real number epsilon that is greater than 0 and go like, heck, are we sure the rest is true, okay? Well, what is the rest? The rest says I would be able to find an m that is a natural number. So what the purpose of m is, the purpose of m is to serve as an index into the sequence. So m is intended as a sequence number, like which number in this sequence are we talking about? So this is basically saying, if you choose a particular epsilon that is greater than 0, and epsilon is a real number, I should be able to choose an m that is a natural number. So now we have two values locked, right? We got epsilon chosen, you choose that. I am going to find a tricky way to choose an m. What about these two values? Such that for all j that is greater than or equal to m, and j itself is a natural number, the following has to be true. What has to be true? K, which is the limit itself, minus x of j, has to be, and then you take the absolute value of that, because I don't care which side I'm erring on, but the error has to be less than epsilon. What does it mean exactly? So it doesn't just say that as I gets larger and larger, we are quote unquote getting closer to k. It is also saying this is approaching in a monotonic way. It doesn't go back. Is that okay so far? As we get, as I gets larger and larger, we get closer and closer to k. Are we doing okay so far with the concept of limit? All right. I asked my son, what he learned in calculus from high school, and the first thing I asked was, so did they talk about limit? No. I go like, how can you talk about calculus without talking about limits? And that's how it was taught in high school, or at least in his high school by that specific teacher. I was actually kind of shocked. It's like, how can you express those concepts? As it turns out, they were not interested about concepts. They just wanted the students to excel in the IB exams. As long as they get a high score in the IB exam, understanding or not understanding the actual concept behind calculus apparently was not important. All right. So note that such a limit may not exist. So I give you a sequence where that limit does not exist. So the sequence is really simple. X of I is just -1, the whole thing to the power of I. So what happens in this case? It oscillates, right? Because when I equals to 0, the value is 1. When I is 1, the value is -1. In fact, for all the odd i's, x of I is going to be 1. For all the, did I say it right? For all the even i's, okay, I think I said it wrong. For all the even i's, x of I is going to be 1. For all the odd i's, x of I is going to be -1. So that means it keeps oscillating. You cannot say that it approaches anything, because this condition here is no longer true. You can pick a particular epsilon. I mean, first of all, are you going to say the sequence is approaching -1, or are you going to say it approaches 1? You got to pick one. And no matter which one you pick, the statement here cannot be true, because it keeps flipping and flopping. It's not monotonically getting closer and closer to k. So the limit of a sequence can also be infinity. For example, if the sequence is defined as x of I is just I itself, then the limit itself is also going to be quote unquote infinity. In this case, the definition of the limit of a sequence is slightly different, because the difference of infinity and any finite number is also infinity, and as a result, the definition needs to be modified as follows. So in the modified version, if the limit of the sequence is infinity, it means Okay, so let's try to read this one and find out exactly what it means. It says right here, for all y as a real number. In other words, pick a real number, and I should be able to find an m such that every j that is greater than or equal to m is going to make this true. X of I is greater than y. Y itself is not infinity because it has to be a specific element of R. In other words, you have something that the sequence itself is always increasing. Okay? And what this statement is trying to say is if you pick a number which represents a horizontal line or the height of a horizontal line, I would be able to tell you where that line intersects with a curve such that after a certain point in the sequence, everything after that is going to be greater than or equal to the number that you have chosen, the bar that you have set. Is that okay? Yep.
How does this connect to time complexity?
How does this relate to time complexity? I think it has to do with what we need to define next. Yep. Because there are certain times we have to deal with the value of quote unquote infinity, and this relates to that. So now we define what is limit superior. In other words, we're just spending a lot of time to define the terms because we need to really kind of understand what does it mean when we say the big O of something, okay? And this is giving us the vocabulary to express what is big O, what is big omega, and also what is big theta. So limit superior, or lim sup, is a series of numbers, x of n as follows. Okay, so we're going to look at this one here. This one may take a little bit longer to explain, so we'll go ahead and kind of go slower with this one. The limit superior as n approaches infinity of a sequence of x is the infimum, which is sort of like the maximum of the, no, this is the minimum. Infimum is the minimum of the supremum, which is the maximum of xk, such that k is greater than or equal to n. Let's see here. Right, okay, this is nested such that n is greater than or equal to 0. So we have two sets notation here. This is one set notation. The membership of that set is using this to describe each element, and this is the criteria of each element. This is the nested set. In the nested set, this is a description of what each element is, and this is the criteria for that particular element. All right. But what exactly does that mean? So there are two ways to read this. You can read it from the inside out, or you can try to read it from the outside in. Most of the time, I like to look at things from the inside out. We look at the most nested portion, and then we expand out. So let's go ahead and do it that way. So we now look at this particular set here, x of k such that k is greater than or equal to n, for some n that is given to me. Okay, well, that doesn't sound too hard, because all this says is, if you think about a sequence, all we are trying to do is to set a particular point of k, of n, and we are basically saying, what is the maximum past this point of the entire sequence? Is that okay? That's what n is trying to specify. N is specifying from this point on, in this entire sequence, what is the maximum? Is that okay? That's the nested set. So with this nested set here, now we have to quantify what is n. So basically, n is greater than or equal to 0, which means we are considering the first number that we are taking the minimum out of is starting from the first element of the entire sequence. We ask, what is the maximum starting of the entire sequence? Okay, you give me a value. Then we move on to n equal to 1, and then we ask, from this point on, what is the maximum? And then we move on to n equals to 2, and then we ask from this point on, what is the maximum? N equals to 3, what is the maximum? N equals to 4, what is the maximum? N equals to 5, what is the maximum? And we keep doing this. So now we have all the quote unquote maximums, from a different starting point, so to speak. And what do we do with all of these maximums? We take the minimum of those things. Is that okay? I mean, do we understand the mechanism first? Okay, because if you are to write a loop to do this, do you know how to write that loop? If I give you an array that is finite, okay, so the sequence is finite, would you be able to write a loop to give me the limit superior of that array? Yeah, it's going to be what, a double loop, right? So the outer loop is going to control where we start. The inner loop is going to say, okay, well, since you have told me where to start, I will start here, and then I will go find the maximum from here to the end of the array. And then the outer loop would collect all of these quote unquote maximums and find the minimum of all of those maximums. That's basically how you do it in a loop, or in a double loop, nested loop. Okay, so what does that do? So what this is doing is, note that even though the limit does not exist, because we have an oscillating function, remember the sequence that oscillates between 1 and -1, we can actually define the limit superior in this case. We can say the limit superior is 1. What does that mean? Why is it like that? Because limit superior is looking at the minimum of the maximums with all the different starting points, right? So, well, with different starting points, the maximum is always going to be 1. So if you take the minimum of all the maximums, it will still be 1. So the limit superior is defined even when the limit itself does not exist. In other words, limit superior gives us a way to define the asymptotic behavior of a function, even when it oscillates. Is that okay? So you can have something that keeps oscillating, but I will still be able to define what is the limit superior of that particular function. But you would not be able to define the actual limit when something keeps oscillating all the time. All right. So limit inferior is kind of the same thing, except we flip all the maximum and the minimum. That's it. So you can look at limit inferior as the maximum of the minimums of the sequence starting at different places. Okay, same concept, except this time instead of looking at the minimum of the maximums, we're looking at the maximum of the minimums.
So is this like worst case versus best case?
Kind of, yes. So you're definitely making the connection between, we're trying to define an envelope where the function f is somewhere within the envelope, but I'm too lazy to find out exactly what the function f is. Instead, I'm choosing and say, this is the upper bound. Now, how is it a gross estimate? Sometimes it is, sometimes it's not. But I can at least say, it's going to be less than this. This is the upper bound. What about the lower bound? Well, it's going to be at least this much. So we're basically saying f of n is at the most this, but at the least this. Because sometimes you may not be able to come back with a very clean answer. Being able to find an upper bound that is easy to look at and easy to estimate and easy to figure out, and a lower bound of the same nature, that may be the best you can do, because you may not be able to get a closed form of f of n. So sometimes we just want to say, okay, in the worst case, how bad can it be? And if your estimate is more pessimistic than it really is, sometimes it's not a problem, okay? Because if you say, I can live with this, I know this is an overestimate of the worst time of this algorithm, but if I can live with this, it will still be okay not knowing exactly what the time complexity is. All right, so now we define what is upper bound, and we are using those terms, okay? And that's why this is like a big, gigantic stack of terms. So we'll start with two functions, f of n, which is the complex function that gives you the exact amount of time to execute an algorithm. G of n, on the other hand, is usually something very simple, like n squared or log of n or n times log n, and it's just an estimate. So now we look at this and go like, f of n is an element of big O of g of n, if and only if blah, blah, blah. Okay, so now we want to look at the blah, blah, blah. This is where the big O notation comes from, by the way. This is the actual technical definition of the big O notation. The big O notation is a set. It gives you a set, and you try to determine whether a specific function is an element of that set of functions or not. Okay? Okay, fine. So what qualifies to be a member of big O of g of n? So we look at the if and only if. So now we have limit superior n going to infinity. In other words, we have a sequence of infinite elements. That kind of makes sense because do you want to define like this algorithm can only handle problems up to n being to the 20,000? Probably not. I mean, we want to be able to say, well, doesn't matter what n is, we'll still be able to describe the time complexity of the algorithm. So we are looking at the absolute value, which is usually not needed because f of n and g of n are typically non-negative, but the definition says, yes, we have to look at the absolute value. F of n divided by g of n, as long as this ratio here is less than infinity, then we call f of n belonging to big O of g of n. Is that okay? Because now we are looking at the asymptotic behavior by looking at limit superior. Remind me again, what is limit superior? It is the minimum of the maximums, okay? Or that's the one way to look at it. It's the minimum of the maximums at different starting point of the sequence, okay, to be more exact. Okay, so if I were to try to describe this in a more natural way, what would that be? Well, we know that limit superior is used here because it can deal with oscillation, right? Because I can still describe, the envelope, with the oscillation. So what is this really trying to say? All it's trying to say is this ratio here is a particular value. It is not infinity. It does not keep going larger and larger and larger. It is a particular value. It is a constant of some kind. Okay? It can be zero, by the way, because if f of n is growing a lot slower compared to g of n, this is going to be zero. So zero is a possible answer. It's not a problem. But in the end, what is this trying to say? Simply said, g of n is an upper bound of f of n. That's basically what this is trying to say. Okay? All right. So now we move on. I do want to finish this lecture. Let me see, how far do I have to go? I'm almost there. Okay. So this is the upper bound. I will skip negligible. So negligible is using lowercase o. I mean, when was the last time you saw a time complexity expression using the lowercase o? Never, almost, right? Because lowercase o simply says it is a gross over a g of n is a growth overestimate of f of n. I mean, why would you want to use g of n when it is just way over what f of n is? In other words, you can say that binary search, which is log of n, is little o of n squared. Okay, n squared is a gross overestimate of the time complexity of binary search. Is that helpful to you? No, not really helpful. So most of the time we don't see little o, but big O is actually important. So now we look at lower bound, okay? So lower bound is almost exactly the same thing. What is different this time? If you look at the membership of big omega or uppercase omega, how is that different from the definition of big O? The comparison. And we are using limit inferior this time. So this time we are looking at the envelope, the lower portion of the envelope, and then we ask, is that greater than 0? So what if it is greater than 0? Well, if it's greater than 0, it can still be infinity because infinity is considered to be greater than 0. It can be a constant, can be 5, can be 16, can be infinity. So what does that mean if the ratio is going to approach infinity when we look at the limit inferior of n? That means f of n is growing faster than g of n, which means g of n is an underestimate, is a lower bound of f of n. That's basically what it means. So the big omega notation is to basically say f of n, or g of n, excuse me, g of n is a lower bound of f of n. Is that okay? So one is the upper bound, one is the lower bound. What if you find something that is both the upper bound and the lower bound? So we are not going to talk about dominant because once again, it is just saying something is grossly underestimating. So that's usually not useful. But when we look at tight bound, this is the ideal case. Okay, we want to find a tight bound if it is possible, because we say that g of n is a tight bound of f of n if and only if it is both the upper bound, g of n is the upper bound of f of n, and g of n is also the lower bound of f of n. So in that case, we have a tight bound, which means we have found a very good way to describe the time complexity of an algorithm. It is not grossly overestimating, it's not grossly underestimating. In fact, it is ratiometrically, it's going to be approaching g of n. Is that okay? So big O is a correct notation, but we also have to kind of keep in mind that big O, all that implies is an upper bound, which can be grossly overestimating the actual amount of time an algorithm takes to execute. So big O is useful, but big omega, excuse me, big theta is actually more useful because this means we are not grossly overestimating. And when you look at the time complexity that we looked at earlier, and I'm not sure whether it's still here or not, I think I may not have that still up here. But when we looked at those time complexity of the sorting algorithms, those were all tight bounds, or at least with most of the algorithms, those were tight bounds. With merge sort, n log n is a tight bound. With insertion sort, n squared is a tight bound. So that's kind of like, if possible, this is what we want. But if this is not possible, we want to at least get to the closest upper bound that we can figure out, in which case that would be the big O notation. Are we doing okay so far with this? So to summarize, okay, I know we are running out of time, but to summarize, the big O notation means an estimate is an upper bound of something that may be complex to figure out. Big omega means it is a underestimate or is a lower bound. Big theta means it is both. We have a tight bound, which means the only variable is kind of like there are some minor things, so it's not strictly like this or strictly like this, but it will be within a very tight envelope defined by the same function, just different by a scaling function, a scaling factor. So you just have to multiply n log n by something. It defines nothing. It's going to take at the most this much time. and then you multiply n log n with a different coefficient that defines the lower bound, the actual amount of time it takes to execute is always between those two curves. And they're only different by a ratio, not by shape. All right, so I think this is a good time to stop the lecture because I think this gives you a new way to look at the big O notation and understand that beyond the big O notation, there are some other notations related to the big O notation. All right, well, you guys all have a nice Thanksgiving, and I'll see you on Monday. Hopefully nobody is gonna be in food coma on Monday. All right.
Hey, Professor.
Mm-hmm.
Yeah, for the, so I've basically done like all the documentation I could think of for the program.
Mm-hmm.
I have no idea